So we're looking at frequently asked questions in Chem 131.2, which is General Chemistry 2. Alright, so we're starting with this first question. This first question is under chemical kinetics, and of course, chemical kinetics is the study of the rate of a chemical reaction, and the route at which a chemical reaction moves to form products is called, of course, reaction mechanism. Alright, so we have a question before us. It's called the decomposition of N2O5 proceeds according to the following equation: 2N2O5 equals 4NO2 plus O2. If the rate at a particular instance is 4.2 times 10 to the power minus 7 molar per second for a decomposition of N2O5, what is the rate of appearance of NO2 and O2? Now, one thing you must know is that in chemical reaction, the chemical kinetics is actually with respect to the rate of disappearance of reactants being equal to the rate of appearance of products. Alright, so when reactants are disappearing, products are appearing. Alright, so basically in this reaction, we need to establish a couple of things. First of all, we need to establish that the rate of a reaction R is equal to the change in concentration all over change in time, which is final concentration minus initial concentration all over final time minus initial time. This is expression for it. But now in a given reaction that we have AA plus BB to give us CC plus DD. This is how a reaction is actually expressed, where the small letters A, B, C and D are used to express the molar coefficient. Then A, B, C, D, the capital letters are used to express the substances. Alright, so in this case, this is what we will do. Now, the rate of disappearance is given as minus 1 over A delta A all over delta T equals to minus 1 over B delta B all over delta T, which is equal to 1 over C delta C all over delta T equal to 1 over D delta D all over delta T. Or basically minus 1 over A rate A equal to minus 1 over B rate B equal to 1 over C rate C equal to 1 over D rate D. Alright, so if you look at the reactants A and B, they have minus. Not necessarily that your final answer should be minus, but in the expression you must put minus while solving. Very important, very important. Okay, so this is the expression. Alright, so disappearance is minus, appearance is plus. So disappearance will always be on the reactant. The appearance will always always be on the product. Alright, so take note of that. Alright, so now we've expressed that. Now let's go straight into solving this question. Now we are being told that the rates, okay, let's express the stoichiometric expression of this reaction. The reaction is 2N2O5 to give us 4NO2 plus O2. Now this would be 1 all over 2 rate N2O5 will be equal to, this will be minus 1 over 2. Now this will be 1 over 4 rate of NO2 and equal to 1 over 1, which is T1, equal to rate O2. The reason why I did not put anything here is because the coefficient of oxygen gas here is simply 1. Alright, so we are giving the reaction to show the relationship between these substances and to get the rate of NO2 from this guy, to get the rate of O2 still from this guy. So we have the rate of N2O5 as 4.2 times 10 to the power minus 7. So this will simply be, now let's look for let's look for the rate of NO2. Alright, let's look for the rate of NO2. So if you want to look for a rate of NO2, we have to relate what we have with the unknown, the known with the unknown. So this will be minus 1 over 2 rate, minus 1 over 2 rate of N2O5, which will be equals to 1 over 4 rate of NO2. Alright, 1 over 2 rate of N2O5 equals to 1 over 4 rate of NO2. So this will be minus 1 over 2. Rate of N2O5 is 4.2 times 10 raised to the power minus 7, which will be equals to 1 over 4 RONO2. Is this guy we are looking for here? Alright, this is what we are looking for. So now basically we have minus we have minus 1 over 2 bracket 4.2 times 10 raised to the power of minus 7. So this will give us minus 2.1 times 10 raised to the power minus 7 equal to 1 over 4 RNO2. We are looking for the rate of NO2. So what do? We cross multiply. This will be minus 2.1 times 10 raised to the power minus 7. Then times 4. Alright, times 4, which will be equals to rate of NO2. So if we multiply, this will multiply minus 2.1 times 10 raised to the power minus 7 by 4. What we'll get here, so the rate of NO2 will be equals to minus 8.4 times 10 raised to the power minus 7. Unit is molar per second. Mind you, units can also be mole per dm cube per second or mole per liter per second. Alright, so this is the rate of NO2, this is the rate of appearance of NO2. Now, like I said, because it is appearing does not necessarily mean that this must be minus. Alright, but you must express your minus from the formula. If 4.2 times 10 raised to the power minus 7 was minus would have cancelled minus to give us plus. Alright, minus would have cancelled minus to give us plus. Now, the next one is B, which is O2. So to get the rate of O2, now we still use the relationship here. So we know that minus 1 over 2 rate of N2O5 will be equal to O2. Alright? Will be equal to O2. So this minus 1 over 2 times 4.2 times 10 raised to the power minus 7 equal to O2. It means that O2 we have already solved it before. This will be minus 2.1 times 10 raised to the power minus 7 molar per second. That is the rate of O2. Rate of O2. Rate of O2. It's important to state that. Alright, so minus 2.1 times 10 raised to the power minus 7 molar per second. Okay? Alright, so we have another question. So calculate the amount of 0.8 mole per liter ammonia left after 300 seconds if the rate constant for the reaction is 2.66 times 10 raised to the power minus 3 mole per liter per second, and also the half-life. Now, it's very important for you to understand when it comes to order of reaction. Alright, order of reaction. We have 3 major orders of reaction. We have the zero order, we have the first order, and we have the second order. How can you actually know the difference between zero, first, and second? Now, zero order has a rate constant with a unit of mole per liter per second. The unit for zero order is mole per liter per second. This is the rate. Alright? For first order, it is just per second. Okay? Then for second order, it is per mole dm cube, then per second. Alright? This can also be mole per dm cube per second. But first order is just per second. So that's how you know. So you don't need to be told the order of reaction. If it is a zero order reaction or first or second, you will know from the units. You know from the unit. Alright? So this implies that this is a zero order reaction because we have this unit. Now let us state our parameter. Calculate the amount of 0.80 mole per liter left. So now you're looking for the final concentration. This is a concentration. Alright? So this is initial concentration A0. 0.800. Now final concentration is what you're looking for. The one left is what you're looking for. Alright, the time taken is 300 seconds. Alright, now basically for the zero order reaction, the formula is A0 equal to AT plus K0 T. This K0 is the zero order rate constant. Your T is your time. Your AT, of course, is your final concentration. A0 is your initial concentration. You're looking for final concentration. Then half-life T1 over 2 for zero order reaction is a concentration of A0, which is your initial concentration, divided by 2K. Alright, 2K or 2K0. all right, divided by 2 times your rate constant. So these are the formulas we are going to be using. All right, so now for this question we are looking for 80. Let's substitute our parameters. So this will be 0.8 to be equal to your 80 is unknown. Plus K naught. K naught here is 2.66 times 10 raised to power minus 3, then times 300, which is your time. Okay, so it means that we have to solve this. So 0.8 be 80 plus, now let's solve this quickly. So we have 2.66 times 10 raised to the power of minus 3 times 300. All right, so this will give us 0.798. So it means that our final concentration will be equal to 0.8 minus 0.798. So 0.8 minus 0.798 will give us 2 times 10 raised to the power of minus 3 mole per liter. This is for concentration. Concentration, either you write mole per dm cube or mole per liter or just molar. So this is the answer to the final concentration of ammonia. So you can also represent this A. You can put in bracket NH3T. All right, to indicate that this is the substance. So we can still say NH3. The final concentration is 2 times 10 raised to the power minus 3 mole per liter. So this is our answer. Okay, so this is our answer. So the next thing we'll be looking for is our half-life. All right, we'll be solving for the half-life. So the half-life here is okay. What is half-life? Okay, half-life can be defined as the time taken for the concentration of the reacting species to be reduced to half its initial value. The time that is taken, it is not the concentration divided by 2, it is the time that it will take for that concentration of the reacting species to be reduced to half its initial value. All right, so it means that our T1 over 2, remember it is our A naught divided by 2K. All right, initial concentration here is given as 0.8, 2 times 2.66 times 10 raised to the power minus 3. So 0.8 divided by, let's solve that quickly. So 0.8 divided by 2 times 2.66 times 10 raised to the power of minus 3. So this will give us, so this will give us 150 seconds. So it means that the time taken for the initial concentration, which is our A naught, to reduce to half its initial value is 150 seconds. It's 150 seconds. All right, so we have a question here. Activation energy of the reaction was found to be 2.04 kilojoules per mole. If the rate constant at 40 degrees Celsius is that, calculate the rate constant at 55 degrees Celsius. Okay, so the formula for activation energy that expresses the activation energy is log K2 all over K1 equal to EA all over 2.303 R bracket upon T2 minus T1 over T1 T2. Alright, so this is the formula for the EA, activation energy. Is EA that is used to denote activation energy. Now your K2 and your K1 are your rate constant, final rate constant, initial rate constant, final temperature, initial temperature. So now in this question we are told to determine the rate constant at 55 degrees Celsius. Let's take our parameters. Now our K1 here is our first rate constant. Now the activation energy of the reaction is found to be this. Now let's do the parameters based on how the question is. Now EA is 52.04 kilojoules per mole. For us to convert EA, all right, in kilojoules per mole to joules per mole, we have to multiply by 1000. So this will be 52.04 times 10 raised to the power 3 joules per mole. You must express it in joules per mole. All right. Then another one is that, okay, if the rate constant at 40 degrees Celsius means that our first temperature T1 is 40 degrees Celsius. To convert from degrees Celsius to Kelvin, you say 40 plus 273, which will give us 313 Kelvin. All right. Now, is this, so this happens to be our K1, 5.76 times 10 raised to power minus 3 mole per liter per second. Now, T2 is 55 degrees Celsius. 55 degrees Celsius, so 55 plus 273, 55 plus 273 is equals to 328 Kelvin. Alright, so it means that we are looking for our K2, which is our rate constant at this point. Alright, so now quickly we have to do what will enable us to make our K2 select the formula. This is the formula. Now K2 all over K1 equals to EA all over 2.303 times R. So your R is 8.314 joule per mole, okay, joule per mole per Kelvin. Alright, so now we'll be imputing our parameters into the question. So our formula first of all is log K2 all over K1 equal to EA all over 2.303 R, then T2 minus T1 all over T1 T2. Alright, so basically we are looking for K2. K2 is what is unknown here. Alright, K2 is what is unknown here, like we said. So let's put our parameters. So we have log, okay, our K2 is what again? Our K2 is unknown. Alright, our K2 is what is unknown, right? Okay, so K2 over, what is K1?
5.76 times 10 to the power minus 3 per meter per second.
Alright, so that is our K1 divided by, what is our EA? We converted this to joule now by multiplying by 1000. So what is it?
2.0
Times 10 raised to power minus, times 10 raised to power 3. Alright, times 1000. So this is 2.303 times 8.314. Bracket to now T2 is 328, right?
Yes.
T1 is 313, right? Then this is 313 times 328. Alright, so we have log of K2 all over 5.76 times 10 raised to power minus 3 equal to, now let's divide this. In fact, let's just divide it, then multiply by this as well. So let's just do everything together. So we have 52.04 times 10 raised to the power of 3. Okay, times 10 raised to the power 3 divided by 2.303. 2.303 times 8.314. Okay, then bracket open. 328 minus 13 will give us 15 divided by 313 times 328. Okay, so this will give us 0.397. So everything here will give us 0.397. So we have to take the antilog of both sides. So it means that we have K2 all over 5.76 times 10 raised to power minus 3. Antilog will cancel the log here. So this will be antilog of this 10 raised to the power of 0.397. 10 raised to power 0.397. So this will give us 2.49. All right, so it means that our K2 all over 5.76 times 10 raised to power minus 3 will be equals to 2.49459. All right, so when we cross multiply, K2 will be 5.76 times 10 raised to power minus 3 times 2.49459. Okay, so this will be times this, so 5.76 raised to power minus 3. So we'll have 0.014. Okay, 0.014 will be our answer, which is 1.4 times 10 raised to power minus 2. And of course, the unit is molar per second or mole per liter per second. Since we are looking at rate constant, all right? Since we are looking at rate constant. So basically, this is our K2 for this reaction, all right? So we have another set of questions. These ones are under chemical equilibrium, okay? And when we talk about chemical equilibrium can be defined as the dynamic process in which reactants, okay, form products and in a forward direction, and a reverse reaction occurs at equal rates. That is, when you say equilibrium has to do with balance, all right? So when in a given reaction, reactants actually form products. And the rate at which the reactants form the product is still the same rate at which the product will come back to form reactant. That is what we call chemical equilibrium. Alright, that's what we call chemical equilibrium. So we have questions here. Chemical equilibrium has to do with what we call equilibrium constant. So these questions, they give the equilibrium constant expression for the following reaction. Now, normally, chemical equilibrium has Kc, and Kc normally is equal to Cc dd. These are concentrations. Anything in square bracket is a concentration. Anything in square bracket is a concentration. Remember, all these things come from this AA plus BB to give us CC plus D. Remember, I introduced this in chemical kinetics. The only difference is that here we have double arrows. These are double half arrows to indicate that it's a reversible reaction. Alright, so now K is equal to CD and all over AB and all of that. So basically, C and D are the products, A and B are the reactants. So if we are to write the equilibrium constant expression for this, you need to also know that these small letters are actually here to denote the molar coefficient of the reaction. So it means that Kc here will be equals to your C. We have only one product here, which is NH3, and NH3 has molar coefficient of 2, so you raise it to the power of 2 divided by, of course, your first reactant there is hydrogen gas H2 raised to power 3, and of course N2 raised to power 1. There's no need writing 1 here. So this is the equilibrium constant expression for that reaction. Now the next question, given that the concentration equilibrium constant Kc at a certain temperature is 0.52 for the equilibrium reaction, okay, so I think this is a continuation of this, alright, this is a continuation of this. Alright, so it's a write an expression for it and calculate the concentration equilibrium constant for the equilibrium reaction below this one. These questions are connected, alright? These questions are connected. But first of all, you'll be given Kc for this. You're told to find Kc for this. This is what we call heterogeneous equilibria. Alright, where you have another equilibrium reaction amalgamating from the initial, trying to create a relationship between two equilibrium constant expressions. Alright, so now basically this is one, this is another. The Kc for this is 0.52. We are told to now look for the Kc for this one. Now the first thing you need to look at look here is this reaction reversed of this? No. They're actually on the same side. N2 and H2 are on the same side. NH3 is on the same side as that one, right? It's not reversed. Now if you reverse one equilibrium reaction, for instance, now if I come here and I reverse this reaction, you will now have 2 NH3 to give us N2 plus 3H2. If I want to get the Kc for this reaction now, I will have to do 1 over 0.52. Whatever it gives me is the Kc for this. That is if it is reversed. If they told us to look for this. Now another thing now is that if this reaction now we are to be, let's say, 4NH3 to give us 2N2 plus 6H2. Now if you look at this now, you realize that the thing that is common, and you still want to use this reaction to compare with this. The thing that changed here is that first of all it was reversed. Secondly, everything here were multiplied by 2. Are you getting it? Everything here were multiplied by 2. Okay? Everything here were multiplied by 2. Look at NH3 was 2, now it is 4. N2 was 1, it is 2. 3, 6. So everything here will multiply by 2. So in this case now, not only that it was reversed, it was multiplied by 2. So what you have to do now is that you have to first of all solve for it when it's reversed. So 0.52. Now you now have to raise it to the power of what was used in multiplying it to get to this point. What was used in multiplying these guys to get to this point was 2. The common factor was 2, so you raise it to power 2. Whatever you get to be your answer. So it's important to state that the factor that actually multiplies the original reaction to get this one must be raised to the power of it. The reason why we took the inverse, alright, the reason why we took the inverse, remember, is because it was swapped. This is just an instance. I'm just giving this one as an example. I've not yet solved this one. I've not yet solved this. Alright, so you think that whatever you get here will be your answer. So now let us come to this the actual question. The actual question. So if you look at this now, it was not even reversed. Alright, it was not reversed. It's still the same. But the only thing is this, if you look at it very well, you realize that 4/3 was multiplied. Are you seeing it? 4/3 was multiplied. 4/3 was multiplied by 3. See, 4/3 times 3. 3 you cancel 3. That's how we go 4. 4/3 was multiplied by 2. 4 times 2, 8. 8/3. That's why we have 8/3 here. So you have to check for the common factor that multiplied the original reaction to generate this. So at this point and at this point now, the Kc now. So the Kc for this now will be 0.52 raised to power 4/3. Raised to power 4/3. We would have done 1/0.52. That is if this reaction was swapped. But if it's not swapped, you just do 0.52. Alright? You just do 0.5. Then raise it to the power of what was used in multiplying. So we say 0.52 raised to power 4/3. Alright? Raised to power 4/3. So this will give us 0.418. This will give us 0.418, which approximately 0.42. So that's the answer. So that's the case to this question. So I need you to be able to understand how to navigate through heterogeneous equilibria and even normal equilibrium constants. Okay? So we have another set of questions still under equilibrium constant. Of course, chemical equilibrium generally. Now it says the equilibrium constant for the reaction. This is the reaction 2NO plus Cl2 giving us 2NoCl2. At 500 Kelvin is 2.27 times 10 raised to power 3. Use the data to determine the equilibrium constant of the reaction, following reactions at 500 K. Alright, so this is Kc for this reaction. Alright, it's still based on what we are talking about. Still depending on the previous question we solved. This is the main reaction with the Kc. So we are told to look for Kc. Don't mind this 500 Kelvin rather. You're not using it for anything here. Alright, so you're looking for I and II. So if you look at this first reaction, relating it to the other, you realize that the reaction was swapped. The reaction was swapped. So it means that for the first one, your Kc now will be 1. Remember, I told you that whenever it's swapped, and it was swapped, it was nothing changed about it too. Alright, nothing changed about it. It's still 2NoCl, 2NO and Cl2. Nothing changed about it. So this will just be Kc all over 1/2.27 times 10 raised to power 3. Alright, so let's solve that. 1 divided by 2.27 times 10 raised to power 3. So this will give us Kc will now be equals to 4.405 times 10 raised to power minus 4. This is the new Kc for this particular reaction. Then for the second one, if you look at it, it was not swapped, right? The second one was not swapped, rather it was multiplied. If you look at it, it was multiplied by 1/2. How you easily know what it was multiplied by. Check the one that had just 1 mole in the original reaction. Then check the new one. Whatever the coefficient is there. Like for instance, now the other one, how we knew that it was multiplied by 4/3 was because N2 was 1 mole. Then the next one was 4/3. And one thing you need to understand is that anything that is used in multiplying 1 is the same thing that was used in multiplying all of them. So as 1/2 was used in multiplying Cl2, it's still 1/2 that was used in multiplying this guy. 1/2 times 2, 2 cancel 2. That's why we have 1 here. The same thing, 1/2 times this guy. But now if you look at this end, okay, it was not swapped, was it? It was not swapped, right? It was not. N is here, Cl2 is here, NOCl is there. The only thing that happened here is that it was multiplied by 1/2. Therefore, it means that our Kc now will just be 2.27 times 10 raised to power 3 raised to power what? 1/2. Because it's 1/2 that was used in multiplying. So we say 2.27 times 10 raised to the power 3. Now raised to power 1/2. So this will give us 47.64. This will give us 47.64. Alright, 47.64. So this is our answer. Now let's do the last one. Okay, let's do the last one, not the least. Okay, I'll be cleaning off this. Cleaning this up so you can be able to have enough space to do this question. Now, a mixture of 0.5 mole of this, 0.5. So let's just use the parameters. We are told that hydrogen has 0.5 mole. Okay, nitrogen is 0.092 mole, and ammonia is what? 0.092. No, this is 0.34. 0.34 for nitrogen. Ammonia is 0.092 mole. All right. Now in a 2-liter flask, so volume here is 2 liters. Now was found to be present in equilibrium at a certain temperature. Calculate the concentration equilibrium constant. So we are looking for Kc. All right, at this temperature. So look at the reaction. So it means that this hydrogen was actually H2. This one is N2, nitrogen N2. Then ammonia is NH3. Alright, ammonia is NH3. So it means that now we are giving the number of moles for each of them. Now it's important to note that for us to get Kc, remember, for us to get Kc, the expression for this that we need, Kc will be equal to NH3. Remember, it is product over reactant. NH3 all over N2, then H2 raised to power 3. We don't even have their concentrations yet. But we can actually get their concentrations. The concentration is mole per liter. Mole per liter. That is number of moles all over the volume. So we have to now to get the concentration of hydrogen gas now. Remember, I told you it is moles per volume. Moles per volume. Number of moles of hydrogen is 0.5 divided by 2. So 0.5 divided by 2 should give us 0.25. So this is 0.25. So 0.25 mole per liter. So that's the concentration. Now for N2 is still of course moles per volume, 0.34, still divided by 2. All of them have the same volume of 2 liters. So 0.34 divided by 2 will give us 0.17 mole per liter. Then our ammonia NH3 is 0.092 divided by 2. So 0.092 divided by 2. So this will give us 0.046. This will give us 0.046 mole per liter. Alright, so we have been able to get the concentrations as simple as that. So the next thing is for us to now solve. The next thing is to solve this exercise. Get our Kc now, very simple. So our Kc now will be NH3, concentration of NH3 is 0.046 raised to power 2 divided by concentration of nitrogen gas 0.17 concentration of hydrogen gas 0.25 raised to power 3. All right, so now let us quickly solve this. So let's quickly solve this. So I'll just put everything in my calculator at once, so we will not spend much time on this. Okay, then 0.17 down, 0.17 down, open another bracket, 0.25 raised to power 3. So the answer here is 0.7966. So we have 0.7966, or approximately 0.8.